Pardon, il y a une diffusion de 30 secondes.
Dear Victor Grimblatt, the board is now fully completed, and I have the honor to be the chair of this board. So let me introduce the board to you and to the people looking at us on the video. So the board is first made of the reviewer that allow you to go to the defense, starting with Giovanni Di Micheli, who is professor at the École Polytechnique Fédérale de Lausanne, and Andrei Vladimirescu, that came from Institut Supérieur d'Électronique de Paris and also Berkeley in California. The board then is also made of Antun Domik, who is with us by video, who is from Synopsys, and Danilo De Marchi, Danilo De Marchi, who is a professor at Politecnico di Torino in Italy, just to mention, in case no one knows where is Torino. And the local guy that was your advisors, starting with Guillaume Ferré, who is an associate professor at Bordeaux INP, François Rivet, who is an associate professor at Bordeaux INP as well, and your PhD advisor and director de thèse, Christophe Jego, who is professor at Bordeaux INP. And finally, myself, Yann Deval, who is also professor at Bordeaux INP. So the word is yours. Victor, you got 45 minutes to present the work you have went up, which is étude et conception d'un circuit numérique dédié aux objets connectés pour des applications agricoles.
Okay, thank you very much for the introduction, and I would like to say hello to the board and to all the people that is looking this presentation. I really appreciate that you are here, and also Antun, I really appreciate that you are connected, being considering the fact that it's almost midnight at your place. So thank you for that. So to start, we are going to talk about the design of an integrated digital circuit for the Internet of Things applied to the agronomy. So the history started a few years ago when I decided to put some crops on my countryside home. So I put some crops, lettuce, tomatoes, and start irrigating that, continue irrigating, the sun was there, everything was perfect, but after a few days or after a couple of weeks, some of the crops died. I was surprised. I said, what is the problem? Why we have this kind of things? And I realized that plants need more than water. Was my first conclusion. And after discussing with some colleagues from the agronomy schools that I have been working with them, they told me that we are far away from the smart irrigation. Why? Yes, it is very complicated to do a real smart irrigation. And another professor told me, so tomatoes and lettuce, they're all different. You cannot compare a tomato with a lettuce. You cannot consider that they are identical for the, if you start considering. So I will outline what I'm going to present, the problem, the solution, or the first step toward the solution, because I think we still have a lot of work, and this is the reason I put future work towards the solution. So the problem, the first thing we have to consider on the problem is the population is growing. Even despite the fact that the growth rate is going down, the population is growing. We will be almost 11 billion by the end of the century. We will be something like 9 billion, so 10 billion into 2050. So we have the first consideration that the population is growing. The second part of the problem is the arable land, meaning the land that can be used to do production of food, is decreasing. And if we measure hectare per person, we were almost at 0.4 on the 60s. Right now it's 0.2 hectare per person. So we see that we have more people, less place to do food. Climate change, we all know that. We are seeing the consequences of the climate change, and we can think that climate change is a major challenge for agriculture. But on the other hand, agriculture, forestry, and the change of land usage is responsible for 1/3 of the greenhouse gas emissions. So on one hand, we have the agriculture is depending on the climate change, is being impacted by that, and on the other hand, the agriculture is one of the major contributors to the problem. And I have also found that a couple of years ago that I really like it is the donut economy and the planetary boundaries, and it's very related to my work. So this is a new way of seeing the world, of seeing the economy. So you have a donut, this is the green part, and the lower limit of the donut is based on the United Nations Sustainable Objective, meaning the humans, meaning that food, education, living, houses, and all that. And the upper part of the donut is based on the planetary boundaries that was created by the Stockholm's Resilience Center in 2009. That is the resources of the planet that we are using. And we can see there that some of them are on the red part, meaning that it's critical, and they are based on what the agriculture is doing. For 2050, current agricultural production needs to be increased by 70%. That is coming from a United Nations Food and Agriculture Organization. And the fresh water, which is agriculture, is the heaviest consumer of the planet available fresh water. We can think in a lot of places that mining companies or industries is the heaviest consumer. It is not, it's the agriculture. And you see there that Europe is very well balanced, but Latin America, where I'm coming from, is not too balanced, and some part of Asia or Africa are not balanced at all. We are using almost 90% of the fresh water in agriculture. Farmer distribution, and this is very important because part of my motivation is to work with the small and medium farmers. 80% of farms operate on less than 2 hectares. About 500 million worldwide farms are smaller than 2 hectares. In the poorest countries, 70% of land is operated by farms that have less than 5 hectares. So if we start thinking of technology for them, 2 hectares, small farms, poor people, it's complicated. And small farms are not adopting technology. That's another motivation that they need. Use that. Too expensive. That's the first point. Too expensive. Hard to use. Farmer digital skills. If you go to the countryside, you go to there, I know this is maybe to exaggerate, but they can use WhatsApp, maybe Facebook, but if we start looking about drones, satellites, that's work. And the communication availability and cost. Because we don't talk about 5G, 4G, but in the countryside, there is not even 1G sometimes. So summary of requirements, which is the problem. So we see that we have more population to feed, less arable land, climate change, less fresh water, ecological footprint, low cost, low power, easy to use, and able to communicate. And we have the agricultural dilemma. This is something that I have thought about that. The agriculture have to increase the productivity while we take care of the planet boundaries. So how to increase productivity, taking care of the planet boundaries or keeping safe the planet. So the first thing, how to solve it. And my conclusion at that time, IoT to the rescue. So let's use Internet of Things to try to solve the problem, IoT to the rescue. But to better understand the problem, the growth and health of plant is a very complex system depending on several physical and chemical parameters. And we can divide those parameters at least in 3 parts: the plant itself, the soil, and the environment. So we can consider the model of growth of a plant is a function that depends on these 3 main areas: plant, the soil, and the environment. For my work, I have not considered the plant itself, though I will concentrate mostly on the soil and the environment. And I know that, for example, at Polytechnic di Torino, you are working on the plant itself. You are trying to do measuring things like that. I will concentrate myself on the soil and the environment, which is a non-invasive way to do the things. So the soil, we have several parameters that could be important for the plants. The texture, which that is the kind of soil we have, the clay, the sand, and so on, the water, the humidity, the nutrients, the potential of hydrogen, the pH, the temperature, soil temperature, and also the salinity. Those are some of the parameters you can consider for the growth and health of plant on the soil. So we can think on a function that depends on all those parameters, but of course we have to consider that the function could be a polynomial, could be exponential, could be linear. We're still investigating that function. The environment, we have the light, the environment temperature, the weather, and the air relative humidity. So we can also consider a function of these parameters to come back to the main function that we were thinking about, the growth and health of plant depending on the soil and the environment. So this is the list of relevant parameters to consider in my work. There are others. I'm not saying this is the only one. There are others, but this is the one I have considered. So the category is soil environment. I have the water, the nutrients, pH, temperature, salinity, and on environment I have the light, temperature, the weather, and the air relative humidity. And what is important is the type of parameter. And I have divided on fully dynamic and partially dynamic. A fully dynamic parameter is a parameter that is changing, constantly changing. For example, like the water. You irrigate, you have a change on the most. Another one that is fully dynamic is the temperature of the soil. It's changing based on the condition of the time, of the humidity, and so on. But there are some that are partially dynamic. The nutrient, they don't change too often. You have to fertilize to change the nutrient. Or the pH, you consider the pH is not supposed to change too often. So this is the reason I have considered. And the third parameter, the third consideration is can we modify artificially these parameters? So for the water, yes, we can irrigate and we have more most. Nutrients, yes, we put fertilizer. But for example, the weather, we cannot change, we cannot impact that. Or the light, it can only be changed if I am in a greenhouse. But if I have my crops outside, I cannot change it. The light is the light, same for the air relative humidity. In a greenhouse, I can do a lot of change. So those are the things to consider that we have. So the parameter, the type, and if we can modify it. Can we measure all of them? That's a great question. So let's go into the solution and how to measure them and how to mix all those parameters to work. So my proposal of the solution, the first step, is a smart agriculture and IoT for small and medium farmers. So the outline of this part will be the system, what and how to measure, a lab at home. I say at home because there was the COVID in the meantime, so I was unable to go to the land to do the measurement. The SOC, system on a chip, and the agri-food community. So the system, it will be an IoT-based system with an ADMS node, ADMS, automatic device making, automatic decision-making system. So just to remember, this is the main IoT architecture. I suppose you maybe know that. So we have the devices, we have the low power, low range network that will send the data to the gateways, and the gateways will send the data through the internet to a data center, the cloud, and we can process that and come back to give some information to the device. But on the same time, in my consideration, I have said that we have to do edge computing because I don't want to send all the data to the cloud and wait for the data. So I will do on the device a lot of computation. So we are now going to concentrate on the device, and the main requirement for those devices are low power because we are far from energy source. It has to be able to send and receive data because we are far from internet connection. It has to be able to process data at the edge computing. It has to be low cost, intended for small and medium farmers. It has to be easy to use of digital skills, and it has to be able to handle several sensors because we want to cover all needed parameters or a maximum parameters based on that. So a conclusion was an SOC is then needed. So we need to do a specific chip to be able to meet all those requirements and to be sure that we can handle the solution we are trying to implement. How to do it? A system to monitor crops. So the components of the system will be a system on a chip, will be peripheral IOs, where we are going to connect the sensor and actuators, LoRa as communication protocol, and a battery, because we are far from the from power source. I can add here, but for the moment, I'm not considering that it is necessary at that level, maybe some solar panels to give some energy to the battery, but I will go into detail of that the battery will be, a good battery will be enough for a certain amount of time. How it works, get data from sensors, measure parameters, process the data in the edge, drive actuator, receive information, for example, the weather from a weather station, send information to the cloud, and send analysis and results to the farm. So even despite the fact that we are going to do edge processing, we are going to send data to the cloud for further processing, further analysis, and further statistics. What and how to measure? The measuring condition has to be easy to measure because we are going to work with some, and we are in the middle of nowhere mostly. The cost of measurement has to be affordable to small and medium farmers. The timing of measuring, periodicity, how often we have to measure the water, the most, how often we have to measure the pH, how often it will change. Accuracy of measurement, sensor accuracy and positioning. What is the distance between two sensors when we are going to measure humidity, for example? 1 meter, 2 meters, 3 meters. So it will depend. I can immediately say it depends on the texture of the soil because if it's too sandy, the water will go deeper immediately. If it is more clay composition, the water will go in that direction. So it's very, so, but it is important so to define the accuracy of the measurement. Able to work on ADMS IoT systems, so the sensor have to be able to provide information in real time, edge computing, and low power. Sensor selection, so I have worked with some sensors to do my experimentation. So moisture, I have found two kind of sensors, the resistive and the capacitive. They can be in ADMS, they are real time, the cost is very low. The main difference, the resistive sensor is more, will get corrosion faster than the capacitive one. So the accuracy of the capacitive sensor is going to be much better, and I will talk later that we are doing some experiment about to compare these two sensors. Nutrients, that is a little more complicated, it's more work is needed. The way to measure the nutrients, especially the NPK, nitrogen, potassium, and phosphorus in the soil is based on the reflection of the light. The reflection of the light, and it is detailed on my manuscript, the reflection of the light will provide different bandwidth based on the way it will provide based on the amount of nutrients that are there. So the red is, for example, nitrogen, the green is the potassium, and so on. Soil pH, that is a big problem. There is no low-cost sensor that could measure pH directly on the soil so far. I know that some people are working on that in Australia and also in the University of Cyprus. Professor Marius, they are working on this kind of things because you can measure pH on an aqueous solution where you have water or something like that, but if you go directly on the soil, we don't know exactly how to measure that. Soil temperature, yes, there is the digital thermometer, DS, this is the sensor I have found. It's very good to use, it's very easy and low cost. Salinity, that is measured through the electrical conductivity, is also a problem. It's too expensive, so we have to look for a low cost sensor. Environment line, it's a phototransistor. There you have some reference. Environment temperature, we can use the same digital thermometer. And environment weather is coming from a weather station, so we don't have a sensor, but we get information from the weather station. So lab at home. So what I wanted to do is to test several experiments were conducted in a balcony at home in Vitacura in Santiago. The experiments were done on Arduino Uno, used moisture and temperature sensors, the one I presented on the previous slide. The experiment is done in spring and summer 2020, 2021, and fall 2021. And the objective was to look how the sensor worked, the kind of information they were providing, and also to start validating the interrelation between parameters and to start thinking on this function I have presented at the beginning, how to interrelate and how they interact. So the first experiment we started in spring, so you can see on the red cycle the sensor inside the pod. So measure soil moisture with a resistive sensor, soil temperature. It was a 4-day experiment. And the objective were to analyze the interrelation of parameters and analyze how is the passage from wet to dry. What is happening, how often, and so how long. So this is some results. So you have the soil temperature that is following a sinusoidal way. And it was I like it. And on the bottom of this graph, you see the passage to wet to dry condition. It took 2 days. So when you start thinking that you have to irrigate your pots at home, it's not every day. It's depend on the kind of crop, but it was 2 days. And on the right side of the screen, you see the soil temperature, the soil moisture and the soil temperature relation, and you can see that we have several points independent of the temperature that under the wet condition, and a moment we move to the dry condition, and we see a lot of points there on the dry part. We can start thinking to use in the next step some machine learning algorithm to start trying to find the relation between soil temperature and moisture, but we can imagine some stuff. When the soil temperature, we are going to see some experiment later, when the soil temperature is much higher, the evaporation is higher, so you are using much more water than when the soil is, when the temperature is going down. So this is one of the reasons that farmers are saying they have to irrigate during the moment that the sun is going down, so there is not too much temperature. Second experiment, the cherry tomatoes. In summer, we measure the soil moisture with a resistive and a capacitive sensor. We start comparing that, measure soil and environment temperature. We are also trying to check the relationship between the soil temperature and the environment temperature. With 3 days, and the objective capture the capacity, compare the capacity and resistive moisture sensor, and to start looking again with the relation between the soil and environment temperature. So the results are there. The first one is on the left is the comparison. The red line is the capacitive sensor, and the blue line is the resistive sensor. For those kind of sensors, the value, exactly the value is not the most important. It's more the range, because the way that you use those sensors is you take the humidity on the water and after on the air, and you do a relation to check the percentage of moisture. But we see that they are very similar and they work together. Now I'm working a very long time comparison to see when they start degrading the measurement. Environment and soil temperature, two interesting things. So the soil temperature, which is the blue one, is following a very good sinusoidal. The environment temperature is having much more changes, less stable than the soil temperature. So we can start thinking that the soil is like a capacitor to store heat. You are going to understand later why I'm thinking of a capacitor, or maybe a resistance for the sensor. Also, the comparison between the environment, this is the environment temperature versus the capacitive sensor. We also see the wet condition and the dry condition and the passage, and of course that has to be put into the machine learning algorithm, machine learning to start looking for the relation. So we already have the environment temperature, the soil temperature, and the moisture, so we can start looking for a relation between these three parameters. Soil temperature versus this is interesting. In the left part of the screen, I start my experiment on a dry soil, so with no irrigation, and you see that during the time that the temperature is going down, the moisture is also changing. So we are seeing the relation again between temperature and moisture. On the right side, I start with a wet soil, so I irrigate first, and it is interesting to see that the moisture is following very, very, very good, but in an inverse way, the temperature. So when the temperature is at low level, the moisture is a high level, which can be a little, we can think this is normal because the lower is the temperature, the higher is the moisture of the soil. Third experiment was a bell pepper at the end of fall, measure soil moisture with a capacitive sensor. I don't have a picture of this, but I forgot to taking measure environment temperature 3-day experiment. Again, the relation between soil and environment temperature and the moisture over time. So what I have here is same kind of relation between soil and environment temperature, but this time the environment temperature was a little more stable, and the moisture over the time, and you can see that I have highlight there, this kind of peaks on moisture, it's at the same time when the temperature is going down. So we have a little increase on the moisture when the temperature is going down. Okay, so based on all that, I started to design my SOC. I had enough information, and I have decided to, first of all, why an SOC? Because you can see, okay, why you need an SOC for that. The first one is a lack of suitable existing platforms. Look, a lot of platforms that they exist, but they are too expensive, or they are not low power, or they don't have enough connection to take all my sensor and so on. So lack of suitable existing platforms. So it is a specific application. It has to be far, it has to be really, really low power, because we are going to put that in the middle of the land. Low power, low cost, and able to do edge computing. So because the reason I have not found a suitable platform for that, even that I have made my experiments with an Arduino, I decided to do my SOC. So this is the design flow I use. This is a classic design flow that Synopsys is advising. I have used Synopsys tools, Synopsys IP, so I use the design flow. So you start creating your project in a tool called Architect, which is a tool to design a processor. You do a selection of all the components that you are going to put on that, the processor, the peripheral, the memories, and so on. You build the first version of the design, and you start simulating that. So you start doing some simulation, you add some C programs into that model to see if your processor will be able to handle, if your memory, the size of your memory is enough to put your and at that moment, when you are okay, you can go into two directions, the FPGA option or the ASIC option. I have more work on the ASIC option. So you replace the model, because until that moment, you are using models for the memory. It's not the physical memory that you are going to implement, but at that moment, you have to put the memory based on the technology you have chosen for your implementation. You do logic synthesis, you verify, you do a static timing analysis to see that everything is okay. If not, you have to change on the logic synthesis parameter, the restriction. You go to the physical synthesis to create the layout. You verify after layout, what we call the post-layout STA, static timing analysis. If everything is okay, you are finished, and you can send your chip to fabrication. This is the two view of the architecture of the edge. So the left one is an overview where you have the different sensors that could be analog or digital, so it has to go through an analog to digital converter, can go directly to the processor. You have on the top the communication, you have the battery, and you can put, and I did that at the beginning, some displays and LEDs to start doing some experiment. And this is the more detailed view of the architecture. You have the SOC, the sensors, the LoRa communication, and the outputs that could be the analog actuator and digital actuators. This is the architecture of the SOC. So it's based on an ARC EM4. This is an ARC EM4 from Synopsys. You have two memories, the ICCM, which is the instruction memory, and this DCCM, which is the data memory. We'll explain later the size of this memory, but you can find more details on the manuscript. I have provided this one. It is important to say that the instruction memory has been divided in two memories. So if we don't have enough memory for the data, we can use part of the instruction memory to put more data. You have the pipeline, and you also have all the input-output I have put. So I have put several input-outputs, so you are able to connect different kind of sensor. There is the ADCs and DACs, there is the UART, the GPIO, the SPI master, the I2C master, and even some PWM if you want to control a motor or something like that. So for the memory consideration, what I have done is to make an estimation of the amount of measurement I'm going to do per day. I'm thinking that I will measure all the sensor, all the IOs every 30 minutes. So it's 40 time measurement per day. So I have made all the computation about the bytes that I need for that. And I got a 8 kilobyte memory. And for the instruction memory, which is much bigger, I put a 64 kilobyte memory. And this is more based on estimation of the program you can put there. And I have also compared with some other platform, and I am on the range of them. Those are the schematic of the SOC. So on the left here, you have the main schematic with the CPU and the memories. The middle schematic is the CPU schematic, and the right one is the memory schematic. Of course, it's very hard to see something there, but the schematics are there. And this is a layout without the paths, because now after I have to connect here the chip to the outside world. So you have on the top the data memory, on the bottom the two instruction memory, and in the middle standard cell that correspond to the processor and the different peripherals. Some values or some parameters of this chip. So you have combinational cells, the number of combinational cells, the number of sequential cells, the number of memories, buffer inverted. What is important is the area. So we have a non-combinational area of 38,780 square micrometer, the buffer inverted area and the memory area. Power. So we were talking about low power, dynamic power, 6.33 milliwatt, and the leakage power, so we are going to consider that mostly negligible. It's 216 microwatt. Critical path, it's important to see whether, because that will give us the clock we have to put in this chip. So we can see that with a clock of 5 nanoseconds, we are okay for almost all the paths. So to be sure, we can put a 10 nanosecond clock to the chip and we will be okay. So it's the first one is mem to register, register to memory, register to register, input to register, and so on. So the longest one is from memory to register. This is the longest path. Energy and battery estimation. I have given some data. No, sorry, that was the. So the total power of the SOC without the paths. We have to be very careful to say that, because paths without add more power is 6.5 milliwatt. So some assumption to make my computation of the battery is a system will read, write, peripheral 48 times a day. Do all my calculation based on that. System will work for 60 seconds when reading, writing IOs. LoRa chip, we took that from the Semtech information, is run at 3.3 volts, and the current during transmission is around 40 milliamps. So the energy during sleep time is considered negligible. So the total energy for that SOC, including LoRa, so for my IoT node, will be around 6.02 milliamps per hour without paths. Again, without paths, so it will be increased. With a 10,000 milliamps battery, the system will be able to work for almost 4 years, considering only the core. So with 4 years, okay? Because really for IoT system, 3 years is enough on batteries. So if I add the paths and the peripherals and so on, I think I can get to 3 years with no problem. So that's another reason why I don't need to put solar panels, because they are expensive. You have to put more money and you have to make maintenance of the solar panel. The size of this kind of battery is a good size, 159 millimeter by 62 millimeter by 9 millimeter. So having a small PCB and a small battery, you can put that on a box, and you can put that. This is the way that we are going to connect the SOC to the outside world. So we have, because the total number of input-output of the core is around 400. And of course, you cannot have a chip with 400 pins because it will be too big. So we have to multiplex or demultiplex the inputs and the outputs. So you can, I'm thinking, my estimation is that 80 to 100 pins will be the right package for this kind of SOC. The agri-food community, so that is a very important part of my work, because when I start this work, I was thinking, okay, I will do a system and I will put that, and that's it. I have found that there is an important community working on this, and I have started to participate, and I think I'm working with some people. We are the pioneer of that. So I started with an ISCA Foodcast as a conference, an ISCA satellite workshop. It was created by Danilo. The Foodcast 2019, I was a speaker. That was my first experience as a speaker on this community. In Foodcast 2020, I was part of the organizing committee, and I present an overview of the problem. And at Foodcast 2021, I was the co-general chair of this conference, and there is more activities coming on that. The second thing that is important is the seasonal school, because we need to start spreading that knowledge to the community, because we have too many people that consider that we just put something on the soil and that's enough. Now we have to start thinking how to sense, how to work, and so on. So we did a first seasonal school, how technology is impacting agribusiness. In November 2020, 19 speakers, more than 100 participants, and this is a book that just went out with all the, not all the presentation, but part of the presentation. So that is my first book. I was the editor of this book, so very proud of that. So now my name is in Amazon and so on, so I was very proud of that. And the second seasonal school will be feeding a growing population, that will be next month. Other initiative ongoing, the creation of a CAS special interest group, more than 30 participants in the first meeting. We are working to have technical and scientific talks, including biologists and agronomists. Again, this problem to include everyone on that. Agri-food conference, so the Foodcast will become an independent conference, and we are planning to start in 2022 in Torino, Italy. We say we are planning, but this is based on COVID, if we have the possibility to travel, if we are independent. And we also got the authorization, at least from CAS and from the Sensor Council, to start having our own journal, Transaction on Agri-Food Electronics. It is a dedicated journal to all this kind of technology that is, I would say it's really started, even that some people have been working for a year, but now we are starting to spread that kind of technology and knowledge. And this is very important. This is also something I put into the community, how technology can help to feed the humanity, but we have to take care of the Sustainable Development Goals from the United Nations and the regenerative agriculture. So we have to do things, but taking into account that we cannot continue destroying the planet. We have to be sure that we do things in the right way, and land usage. We don't need to go overproduction. Over-fertilization, for example. Over-fertilization is destroying the plant, and it's destroying the crop as well. The crops need a specific amount of fertilizer based on the species. So basically, it is lettuce, tomato, and so on. And it is over and under fertilization will decrease the productivity. So my contribution to the agri-food community, agricultural contribution to global warming, other planet issues, and the UN SDG, as I just explained, regenerative agriculture. The other part of my contribution is the lack of IoT and electronic system considered the process of plant growth. So I'm putting into the community this big picture about all the parameters we need to consider. There is a lot of systems that are just measuring moisture that are sold to farmers, and farmers have to say, doesn't work. So why I need technology? I know better than this system. Lack of IoT and electronic for small and medium farmers. Lack of interaction between farmers and agronomists with electronics and system engineers. We have to do this kind of, we have to work with them. They have very interesting ideas. And low level of technification of the agribusiness, especially for small and medium farmers. So to conclude, almost on the time, the future works toward the solution. So what kept me awake? What are the topics that kept my attention during this research work? The first is the lack of low power and low cost sensor for some of the parameters influencing plant growth. Finally, I have found the very good sensor, low cost, low power for moisture and temperature, but for the rest, no. So if we really want to do a good system, a good IoT system, we need to work on sensors as well. And some people are working on that. The second thing is the equation and model of plant growth and interrelation between measured parameters. parameters. That is something that will keep me awake, because we need to continue to work on that and to get into that equation. I will talk a little more in the next couple of times. Better understanding of plant growth for better IoT system. To understand one nice example I gave, we are doing an experiment about with lettuce measuring moisture, and we plant 270 lettuce. 1 week after, we had only 30. So 240 disappear. Birds go in the morning. So this is another thing that we are not considering when we put the IoT system, okay, what we do with birds. And there is a lot of rabbits, birds, there is a lot of things. Pests, so we need to better understand how they work. And there is a lot of study about the feeling that the plants speak, the plants communicate between them, the plants smell. Very, very interesting. Sensor accuracy over time, of course. Other parameters not yet considered, adding more capability to the SOC, manufacturing the design SOC and characterize it and build IoT system and deploy. One of the topics I would like to continue working is the equation and model of plants. Need to capture more data from sensor. Experiments working on experiment at Universidad Santo Tomás in Chile, where we are working with lettuce, orange, and so on. This is the reason we lost a lot of lettuce. Can use machine learning, and my dream, I would like to make a spice model for the growth of plants. Because, and I have discussed that a lot with advisors and so on, we can, for example, think that the soil can be considered as a capacitor to store heat. We can also see that the soil can be considered resistant to moisture, because depending on the texture of the soil, you have less or more penetration of water. The environment temperature can be considered as a sinusoidal power supply. So looking the parameters and trying to put them as an electrical component, we can start trying to do a spice model. So after Andrea, if you can help me on that. This is a very interesting thing that can be very, very good for the future of this kind of work. Better understanding of plants growth for better IoT system. Species is an important parameter to consider. So if you want to really do a system, an IoT system for agriculture, the first parameter to put into your system, what is the crop you are growing? Because they are different. And I have not put the details there, but they are on the manuscript. For example, the nutrients availability depends on the pH of the soil. And it is different for the different kind of species. So some species need a more acid soil, some others are less acid soil. So you have to consider that the species is very good. Other parameters not yet considered, the wind, for example, the wind will impact on the evapotranspiration of plants. Workloads to agronomists, biologists, and farmers, again, we have to. And enhance the capabilities of the SOC, need to finish the paths, manufacture, testing, and characterization. And I'm working 2 projects with 2 universities in Chile to use that chip. The first one will be used by Universidad de la Frontera for a smart agricultural research project. They are working with animals, but they already did a prototype they put on the collar. And I was there with Professor Ferre. You remember? Yeah. Okay. So now they finished, and now they want to implement the SOC to put on the cow. And the other one will be used by Universidad Santo Tomás for a smart agricultural research project as well, for the lettuce and the orange and so on. So we have only just begun. This is a nice song from the time we were kids. I was a kid, at least, from Carpenters and Seneca. Thank you very much for your attention, and open to any questions you have. Thank you.
Thank you so much, Victor, for being so precise with the timing. So let's start with your 2 reviewers, because they agree you to defend your work toward the jury. And the word is now for Professor Giovanni De Micheli from l'École Polytechnique Fédérale de Lausanne.
Mr. President, I ask you the permission to speak standing.
Of course. That's your word.
I will choose a location that's distant enough so that I can cut off my mask. So I would like first to commend the candidate for the excellent thesis that I read with pleasure and interest, and for the excellent presentation that was entertaining as well, full of information about this interesting field. So congratulations.
Thank you.
I have a few questions that I wrote here, starting from the simplest one. You think of a field, a smaller farmer. I would assume, let's say, that he or she has 1/4 of an hectare, which I think it's an acre. How many sensors would you put in an acre? What is the density of what you're going to deploy?
That is a very good question. I will start answering with it depends. It depends on the type of soil. It depends also on the bend, because if you have some inclination, so the water will go down or will go up. So I will start saying that we need to put sensor every 2 meters. I don't speak on acres, I speak on meters. So every 2 meters, but maybe we have to close them or put it farther. But it will depend a lot on the species and also on the type of soil. So there is no a unique answer for that. The first one will be to analyze the soil, that is sending a sample of the soil to a laboratory, and from there get type of soil. The second is, as I say, the inclination, the angle we have, and that will help to define the amount of sensor. But I would say every 2 meters, roughly.
But would you envision to put a chip at every point of your network, or would you just distribute them over the surface?
It will be both of them. So not one chip per sensor, but one chip per certain amount of sensor, depending on the peripherals and the power. Because if I put too many sensors, I will not be able to keep that alive for 3 years. This is what I want. So there is a compromise between the power, the amount of sensor that is accepted by the chip, and also the batteries and the cost. So it will be a compromise.
Let me come to a different type of questions. You know, we're talking a lot about environment, sustainability within smart agriculture. So one of the issues is that you are going to deploy electronics in silicon or encapsulated silicon over a fairly large surface. So how do you deal with the fact that it should not be polluting? How do you deal with, and this is a question at large, goes beyond your thesis, but just to see your vision, that it could be biodegradable, or do you think that there will be a maintenance so that non-working chip will be removed? How do you see the problem of powering them up? Batteries don't look that good.
Yeah,
but
we have discussed that with some agronomists, because there is also the problem where you put the sensor, because you don't have to influence the roots of the plant. So the first consideration is how to put the sensor based on the roots of the plant. Yes, there will be some degradation, and that will also be part of the equation to how often we have to put a sensor, what is the distance, of how many sensors do we need to have a real view of a plantation. Yeah, we have to take care of that because we want to be sustainable, but this is part also of the implementation system research, where we have to measure that and we have to see the impact. But it is also very important to do not influence the growth, because we are touching the roots. We are destroying the environment. When you put a sensor, you are destroying it. At least the close environment to that specific.
I think principle. Measure a plant, then you destroy it. There's obviously something.
There is other methodology of measurement that is invasive and destroys. We need to learn. We need to learn much more. It's the reason I put this is we have only just begun, because we people from electronics, computers, we know how to measure. We know very well how to measure, and we can measure a lot of things. But now we have to be sure that we measure in the right environment, in the right way. And this is Very interesting topic to follow.
But I understand that your thesis has been basically about the device, the sensing, the unit, and my questions are more on the systems, how you would put together any of these. And again, I was just only during the presentation was thinking, well, would the battery be better? Maybe
They will.
A solar silicon-based sensor, whatever, would eventually the chemicals that are in the electronics affect the soil and its solidity. That's a long-term effect.
Yeah, that's an interesting point. Very interesting point.
I have two more questions. One is related to the chip itself. You said that basically that's the measure every 60 seconds or every 60 minutes. Or was it 60 minutes?
Every 30 minutes, I do a measure.
Every 30 minutes. Does the system have a power management system?
Yes.
And how is it? So it's just a circular?
It's a simple one. It's a simple one because we are going to put the chip on sleep mode until we get the measurement time, so just a timer. We can get that. And after we start waking up with different components that we are going to use. Because it will also be dependent on the sensor you have in the system.
But just to pick your brain, in a system that's for agriculture in an open air, wouldn't also make sense to consider, event-driven power management? Because in your environment, probably the biggest event is the thunderstorm that can change the landscape of what's happening unless you're covered. And so, how much would be, interesting to make the power management sensitive to parameters?
I was thinking on that at the beginning, and I decided for the first step to do something that is not event-driven, but more a sequential measurement. So I wake up the system, start measuring, do something, sleep, and come back in 30 minutes. But this is something to consider. Do we work on interruption mode? Do we work in event-driven mode? Do we work in sequential way? But for the moment, I was thinking, and all my computation about memory and so on were considering a sequential way. So a while one, we do a lot of things and we sleep.
I have a last question. Again, it's picking your brain because I wanted to go a little bit farther on. I myself worked in power management many years ago. And I think kind of an analogy. In the end, you have a production system, which is in the open air, where you produce crops. And by using sensors, you can see, what's the performance of that, how they grow. And let's say that you have also a variety of sensors that you didn't mention today, but you could have. And part of the control now is basically the water, how much you use, which is a scarce unit. So one could pose the problem, what is the minimum water that I give to the plants in such a way that they achieve a certain productivity. And of course, this problem is a little bit complex because you couldn't give just, a milliliter per hour or something like this, because otherwise it doesn't help. Water has to be given in distinct form. So my question is, do you think it's reasonable or it's envisionable to have, like this dynamic power management, dynamic water management, change power with water, where you have on one side, a model of your environment that's assuming that again that you're in the open air, it's a stochastic model, tells you when it rains, when there's thunderstorm, when it's dry, which degrades to the system where you have during the day that you've shown, hot during the day, cold during the night. And then you have a response of the system in terms of that, at some point with the terminal, it's the time that I water, it's the time that I stop, and you do this going up to optimize the growth factor. Can you elaborate on that? What are your thoughts?
No, I think that could be a very good thing to do, but once again, we go to the fact that it's based on species, because for example, lettuce cannot go under 60% of humidity. Some other crops can go under just to 40%. The idea will be to be measuring, and moisture is not changing too often, as we have seen in the different experiments. So to measure every 30 minutes, every hour, and act immediately. This is the reason I say we have to have edge computing to be able to act immediately. So if we are approaching the level of water that will be critical for that specific species in that specific soil, that moment we have to start irrigating. And we have to stop when we go over the threshold.
Mm-hmm.
There is a moisture threshold per species. So we have to start irrigating and stop, because if we over irrigate, it's not good.
But the key thing is to start. You can measure it because you know what's the amount that you have to give. The question is probably to guess when it's good time to do the irrigation.
It will be based on this threshold. Because on the other hand, it is not good to provide too much water to the plant. So you have to stress the plant a little, and even there is a lot of research about how to teach plants to be less water dependent because of climate change. So maybe we can stress a little, but we have to be very careful that we don't go down the threshold of moisture, because the plant will die. So my idea, and I have discussed that with agronomists, is to keep the plant in a certain level of humidity. And for that, we have to do dynamic irrigation. It cannot be I irrigate because the temperature is not, the moisture is not good, and after I irrigate, let's say, for 10 minutes, and after I continue, it will be a measurement and decision.
Well, I'd like to thank you.
Thank you very much.
I leave the word to the next.
Thank you, Professor Micheli. And now it's time to give the words to the second reviewers. André Vladimirescu from ISEP in Paris.
Thank you, Mr. President. And I will follow the example of Professor Giovanni De Micheli and stand up, no for other reason than to take off this wonderful mask and breathe. So before all, I take a good breath, and then I want to congratulate the candidate for a very original and unique work, I would consider, because not many people think of the subject you chosen and have with their doctoral work such an important societal impact as you do and all your work. So now, because I need to ask you some questions, let's consider a few aspects. Let's start with the big picture first. So in my mind, I'm asking myself, you have such a powerful chip, SOC, that you have built. And then, this SOC can control tens of sensors. How are you going to position it from a practical point of view? You have an area of tomatoes, lettuces, whatever. Where is the actual controlling device going to be, and how does it connect to the different sensors?
Yeah, the controlling device has to be, we have to have more than one controlling device, because we cannot put the same controlling device in tomatoes and lettuce. One for lettuce, one for tomatoes. And let's assume that we have a land of, and we are doing this experiment right now at the University of Santo Tomas, but we can do it. Let's assume that we have 3 meters of lettuce, 4 meters of lettuce. And lettuce are put every 20 centimeters. So, and we can put, let's say, 3 sensors, maybe 3 meters, for example. We make a test. We put one device, only one, because with 3 sensors we can get one device. If we start now replicating that, the 3 meters, 3 meters, 3 meters, over, there is 1 meter distance between the range of 3 meters. Maybe we can go to 6 sensors in one device, but after we have to put a second device. So it will depend on the distance, of course. I don't want to put a lot of cables, but it will be too complicated and it will be invasive to the crop. That's the first thing. And the second one, it also will be based on the power we are going to consume from all those sensors. So it's a compromise between power, cost, and capability of the device. But the idea is to put more than one device. It's not only one per cultivation. It's to put more than one. And this is the reason that we are talking about low cost, because if we have low course, we can do it.
Okay. Now, yeah, obviously it makes sense to have several sensors on a control device. And then we have to have cables. As you said, we don't want to have many cables. So what do we do? You know, in the field, there are rodents, you know, and some rodents like, you know, mice or squirrels, they love cables. They like to, you know,
That's a big problem. We can do several things. One is like the hard disk when you do mirroring, so we can put two sensors to measure the same, mirroring. And of course, one of the things that has to be in the software is to detect if one of the sensors is not working, not responding. So we also can have like a watchdog, you know, in embedded system, we have the watchdog concept where you are continuously asking your devices, are you alive? You can do something like that. Yes, there is, as I say, there are birds eating the salad, but they can also eat cable. The other thing is to protect cables as much as possible, but if you start protecting too much, the cost will increase, so it will be also a compromise. But yes, and this is the reason we are doing a practical work right now in Chile about this, putting cables on this tube of zinc, where we put the cables inside, isolating zinc towards measure how we can really isolate, because we work completely in the air, so we are putting isolating boxes. So we are doing some tests of that. But it is true that we have to take care of all these things.
Would you consider adding to your SOC some transceiver, some small transceiver that would communicate with the sensors and replacing instead of cables that will pose the problem? Do you see any inconvenience?
It is an idea, but it's also we have to put into the equation the cost. The more things we put into the SOC, the more expensive it will be. So we have to consider the cost of that. But yes, it is an idea, but it has to be taken in account based on the cost.
Okay, so we have to get on this project also some bean counters to figure out the cost and find.
The cost is very important. The cost it's critical for the kind of user we are targeting. It's critical. Some of them in some underdeveloped countries, they get their small production that they eat themselves and what they have. The rest they start selling that. But the cost is critical if you look what is happening in some of the places. And I know that a professor from Israel, Professor Yossi, that is making a very good experiment in India. Cost is must. You cannot forget the cost part of your equation. It's very, very important.
Okay, well, if you know, cost is so important. Obviously, I don't argue it is very important. Let's talk a little bit about the architecture you choose. If memory serves me right, you're choosing an IP of high performance bus and a 32-bit processor
Yes.
for your SOC. Is this an overkill for a system that has to do, you know, a measurement, get some data every, I don't know, 30 minutes or, you know, on a very long time scale compared to like you showed that your clock can run at 5 nanoseconds. I mean, isn't there?
Yes and no. It depends. Honestly, it depends, because if we want to add more computation and more things into the edge, if we start doing some deeper analysis or some predictions or taking into account the weather, for example, coming from a weather station that goes through the LoRa connection to that, we start doing more things. It is not an overkill stuff. But if we just measure a parameter, we compare with a threshold, and we say we act or we don't act. Yes, it is. But doing more things with the chip, no.
All right, it's an optimization issue. Let's see. Well, I have the obvious discussion, but let me see if I can ask you anything else before that. Oh, yeah, an interesting question. You're using 40 nanometer technology.
Yes.
And dynamic operation, what percentage of on a 24-hour scale you're using how much, 10 minutes,
Yes,
right?
yes.
Okay. Now, you put the devices in sleep mode, but these damn small processes, they leak a lot. So I'm interested when the device is in sleep mode, you need to keep some of your memories supplied. So which, in your general architecture, which of the blocks are still supplied in sleep mode?
That will be mostly the main control of the processor to wake up. And of course, we have to keep the memory somebody power to keep the data.
Right,
Yes.
more memory you have, more
Yes,
you need.
we have to keep that. And no, that will be the main block, the one that will wake up and that will have a timer. We have a timer running and also the memory.
Yeah,
But on
so-
the other hand, if we can put solar panel, which is another option, we have less problem. But
Yeah, so anyway, just as a number, it looked to me that the leakage power was very low. It seemed to be.
yeah, that's a thing that also I was thinking about that. Why not to do that chip in 180 nanometers, something like that, because it could be used. So that's another option to study. Can we change the technology to go to a bigger technology, because we don't need 40 nanometers. So 180 will be okay. So,
Okay, and my last point of discussion, my favorite subject, spice.
yes.
So let's see, how can we make spice have an impact on your project? Now, from the modeling point of view, I can see that you have many more kinds of transistors here than we have in technology, right? So in principle, we need to build a model for each of the plants that we want, right? Okay. And you listed a set of parameters like, beyond the obvious temperature, humidity, and so on, like nutrients, what type of nutrients, and so on. So I think that each plant to take a PhD, it is the only thing. So,
No, we can parameterize something because the parameters are the same. The values of the parameter depend on each plant. But the parameters should be the same for the plants.
okay.
But the value of the parameter,
LW such that would cover the lattices and another one and so on. So then we'll have a set of parameters. So that would be great.
Yeah.
Only one thesis.
we have got, okay, we can work together on
We
that.
can work together. I'd
Yeah,
love
of course.
to do that.
I go to see what he said on that. We will discuss that. No, that's a very interesting project, and I agree. It's one thesis.
Right.
But the thing is that today, from what I have researched, because when you start researching things, you don't know if someone else is doing something someplace of the world. But from what I have found, there were some agronomists that work on a model on the 70s and 80s. But after that, I have not found anything about model. And I think it is very important to start considering a model of the growth. And if we can simulate that would be great. So, but it is a long-term project.
Yeah,
It's
I
not
think
easy.
we can do that, and modeling the thing, I don't think would be a big thing, but what about going beyond that? I mean, making spice like a control brain that, it gets new information and gets it into its models and things, and maybe, there is some back-end processing that gives you the new parameters to use.
I will say that this is one of the most interesting topics I have found for further research.
Yeah.
How to do that, because that will help a lot agriculture. Because today, for example, one of the examples, which is not exactly related, but fruit producer, they would love to have a prediction of the production when the tree has the flowers. Right? So if you can count the flowers and predict the production, they will be so happy because they need to prepare the logistic of the production to export and all that. And they have to wait until very close to to the end of the process to start to know the number of fruits that we get. So if we can do it earlier, they will be so happy because that will help ourselves. We have to work on that one hour.
Cheese is number 2.
Okay, I'm going to discuss it.
Okay. Thank you very much.
Thank you very much.
Congratulations
Thank
again,
you very much,
Victor.
Professor
Great
Fernandez.
work, very
Thank you.
interesting and very useful.
Thank you very much.
Thank you. Thank you, Mr.
Thank you, Andre. And we are now going to give the words to our colleagues from California because it's really late at night. Thank you, Anton Domig, for being with us. The word is yours.
You're on mute.
You're unmute. You are muted.
Yeah, I have one comment, Victor, or a sort of question. You mentioned in several places, but not very directly, the effect of the environment, because you say there will be deterioration in the sensors and that, but you do have a temperature range in the field that if you look at places like Western United States, Montana, you're going to be between minus 20 degrees Celsius and plus 30. So at some moment, I think that some special reliability or some, whether in the semiconductor process or something in the architecture that will allow you to operate on those ranges, because I see that as the first part that you would see deploying into the field an electronic system with chips inside. You can protect from the rain, but you cannot have a heated cabins throughout. Do you have any thoughts on that?
Yeah, that's also a very interesting question. I was targeting more places where the temperature has not a so big range.
Yeah, like
So
Quillota in Chile, yes.
Concentrate mostly on the time where the crops are growing, because during winter, the crops are not growing.
Yeah,
So that creates a problem, because maybe we'll have to remove the system and reinstall the
that's
system.
not good, yeah.
Not good. But yeah, that's an interesting question. But the agriculture part is more targeting places where the climate is more stable. Let's say we don't have extremes like.
Yeah, okay. All right, very nice presentation. Congratulations.
For being so late awake. Thank you very much for that.
It's okay.
Oh, thank you. Okay, thank you so much, Anton. And we are going back to the local guy. Please, so Professor Danilo De Marchi, the word is yours.
Thank you. And thank you, Victor. My congratulations for the great work you did, and also because in parallel to your PhD thesis, you really was a key in the community for putting down many actions. Okay, we did, and I'm very proud of it together. So thank you so much also for this. Well, I start from a question related to two things that you put in the first line in 2 slides: low power and the consumption of sensors. So I guess that you started from digital part, of course. It is needed an important starting point. Perfect. So I want to have your comments about the fact that you mentioned that the sensors can kill you in terms of powering and can kill you your application. And the reason of that is that, yes, you have a sensor consuming, but most often are the readouts that kill you. So in this case, we open the door of analog circuits. We open the door to maybe not standard electronics, maybe under threshold electronics. So what do you think that is needed? What you see in the future of the works that we have to do for solving this part of the problem?
Yeah, that's also a very interesting question. This is the reason I put at the end, we have only just begun. It's the first step. When I started 4 years ago, 4 years to do that, I was thinking that with digital electronic, we can solve everything. After 4 years, I'm sure that we cannot. This is the reason we have some things to continue. But that digital solution will help to provide us a low-cost possibility to do things and to start, based on the results of that, we will be able to start doing more things. Today, what we have is a lot of, and I'm only using a lot of Arduinos and Raspberry Pi everywhere, which has more power, more cost. So that will be a first step to go into the next direction, which is let's try to do a specific system. And of course, we have to start, we have to continue looking from the data we are going to get from there to look, okay, how we improve now the system to be able to work under low temperatures, under environment conditions that are complicated and so on. But this is, as I say, we have only just begun. But yes, we have to continue. And this is the reason the community is so important, because sharing information between the community, we will be able to go up and to continue working with that. We don't have too much time, because in 2050 we have to increase the productivity by 70%. So 2050 is in 30 years from now.
So to summarize, tell me, it is that your suggestion is to, as is happening everywhere, to reduce as much as possible the analog part.
So for the moment, yes.
But this is the way.
Yeah. Okay. And also to reduce the size and the power of systems. But today, if you look for a big system getting a lot of data, we don't have. We have a lot of research. I agree, we have a lot of research that you are doing, and Professor Marius and Professor Marco. There is a lot of people researching. But we still need to have a some system that we put everywhere to measure, to get data, to learn from it.
Okay, second question I have is related to a discussion that we had every time that we met in the past, and I want your update. You are expecting what I'm asking you. You had great contacts with agronomists, people on the field. The acceptance of what we are doing, how is it going?
Very low. They don't trust us.
Okay.
And the problem is that we arrive, and this is the way we do. We arrive there, we know how to do. We don't know. And this is the reason, I really put that there from an agronomist. We are really far away from smart irrigation. Because he told me, you don't know how to do smart irrigation. We don't know. We don't know how to do smart irrigation. So there are people specialized in irrigation, people that have done PhDs and postdoc and so on, just on irrigation. So I think we have to be approach them, learn from them, and proposing them, what about if we use that to help you, not to give the solution. That will help them. So we have to start considering that we don't know. We are there to learn. One of my first conversations with one agronomist was, and this is the reason I put lettuce are different from tomatoes. She asked me, what are you going to do? No, I'm going to measure. Okay. On what? Lettuce. No. They are different. Okay, lettuce. Which lettuce are you going to use? Because they are also different. So, and probably electronics. You don't know that. It's not to learn.
Thank you for your word, humble. We must be humble. I fully agree. Well, I have, if I can, another question related to the comment of Andrei about models in SPICE. I don't know if you know the MEMS modeling, Centurion.
Yeah.
So I guess that the way of doing this, I really like when I teach to my students Centurion concepts. They're always excited because it did really something, a step forward, using electrical circuits for modeling nature, because you can model everything. What is inside plants? They are living systems, so more complex than MEMS. So I guess, I don't know which is your comment, but we have really a challenge, but it's interesting to do it, because we want to use the same concept as Centurion did for MEMS, for living elements. No?
Yes. And this is what I'm passionate of that. I'm very excited to work on that because living things, plants, even ourselves, it's, I think, in my opinion, we should be able to model with a lot of parameters, a lot of variables and so on, but maybe we can concentrate on some part of the model. You know, I remember when I started studying a long time ago, the freedom, the grace of freedom when you start putting some variables as constants. Maybe you have to go in that direction because I want to concentrate on that part. But that would be passionate to try to simulate and to model a living entity.
President, if I can, the last one. The last one is related to Nani's question about event-driven. That is absolutely a fact. But we have great, very long time clocks. So here we have living system living for centuries. So they have a similar clock, please, Andrei, if I can, as the one you have when you have dinner. Your clock, you know, very, very slow. So it's a fact that event-driven. But when we as engineers, we think to event-driven, we think of microseconds, milliseconds. In this case, so the time constants, in fact, I have seen you have a temperature changing, but the soil reacts after. So which are the timings that you see are needed for giving a good answer to agronomists in this case?
Complicated question. No, it's, you know, those things don't change too often, too drastically. So I think that if we take, I don't know, minutes or even, it will depend on what parameter. Take minutes to warn the farm, it's okay. The freezing, the one I have not touched there, when the soil is going to freeze, that is more critical. We have less time. But I think minutes or even 30, 45 minutes, it's okay for them. But do not forget that sometimes what they do with these kind of things is that they are outside looking. And of course, the reaction time is also 1 hour. They see, oh, something is coming. For example, the birds problem. We know that the birds problem that eat in the salad are in the morning, very early, when the sun starts to rise. So, you know, that will be a more complicated, but we can do something automatic. Because the way they do that, they do the birds, it's about with noise. They put big noise on the field. So if we can measure in some way that there are birds coming, we can put noise. That has been more immediate, but all those things can take time.
Thank you, and my congrats again. Thank you.
Thank you.
Thank you, Danilo. And we are now going to the local advisors, starting with Professor Ferret. Okay.
Okay, so thank you, Mr. President. So I would like first to thank all the jury members for being here today and also virtual for Workload. Special thanks to the viewers for their great feedback on the Victor Award. Then I would like to thank you, Victor, also for the different exchange that we had during your PhD. I think for François and Christophe, it was a first experience to supervise a PhD student, I think, with more experience than me. So I have to be humble, as you said, during the different exchange. I have a question. Just I think that your work is a very interesting contribution that opened the doors of many fields as we discuss the different models and so on and so on. Thank you for all the discussion in virtual, in Chile, in Santiago. It was for me a great experience with. I hope that in the future we can continue to work together, probably to supervise a PhD, and now to together. So I know that François prepare or will explain the stories of why we are here today. So I will let François gives all this detail in order to precise why we are now today together for your PhD. Thank you, Victor.
Thank you, thank you.
Thank you, Guillaume. And the word now is to Professor Rivet. François, please.
I've taken notes.
It's a long story.
So, thank you, Mr. President. First of all, I would like to thank all the committee for your participation and to have attended either in person or so late virtually. Then I would like to congratulate you, Victor, for all this work during the past 4 years. You did investigate on a unique subject, mixing electronics, but also communications with IoT, and of course, agriculture. All your insights are of great quality and, let's say, fruitful to the circuit and system community, but also for the community, you have contributed to create and gather. As you might imagine, I know your work very well, and thus I won't have any question related to it. So now, if you agree, Mr. President, I would like to switch to French. Donc, merci Victor pour ta présentation et pour tout le travail que tu as réalisé ces 4 dernières années. Je ne te cacherai pas que c'est un réel plaisir de t'avoir accompagné dans tes réflexions. Tu as mis un point d'honneur à faire cette thèse, ta thèse, dans les règles de l'art, en redevenant un jeune étudiant. Tu t'es plié à l'exercice avec sérieux et je salue ici ta performance d'avoir pu assurer à la fois une riche vie professionnelle et un travail rigoureux avec la construction de ton sujet, des expérimentations, la conception d'une puce, la constitution d'une communauté, l'écriture et la publication d'articles, et enfin l'écriture d'un très beau manuscrit. Je suis très fier d'avoir mon nom associé à ton travail. Je me permets maintenant de faire un petit rappel historique. Alors en fait, ça commence à la machine à café de l'INSERM en 2004. Tu n'étais pas là. Mais il y avait un Chilien qui n'arrivait pas à se servir de la machine à café. Il s'appelle Juan Pablo Martinez Brito. J'étais étudiant et je l'ai aidé à faire marcher la machine et on est devenus amis par la suite. Et c'était le premier Chilien que je rencontrais de toute ma vie. Puis, le hasard faisant, lors d'une conférence à Curitiba en 2013, ce Chilien m'a fait rencontrer mon deuxième Chilien, toi. Là, nous étions dans une churrascaria et c'était avec Yann. Je me souviens très bien, je nous revois encore au milieu de la churrascaria. Alors, tu nous as tout de suite parlé en français et ma première remarque a été « Mais tu es français ?» Et là, tu as répondu « J'ai fait mes études en France, à Poitiers, et j'ai ma nièce qui vit à Pessac. » Vous ne pouvez pas faire plus local, ça c'est sûr.
Tout à fait.
Et le courant est tout de suite passé, et de conférence en conférence, nous sommes devenus amis, avec des discussions toujours passionnantes, autour d'un verre de vin, bien évidemment.
Pessac, Bordeaux, Chili.
Ensuite, fin août 2017, on est sur la plage de Fortaleza, dans le nord du Brésil, et là tu me confesses que tu n'as qu'un seul regret dans ta vie. Tu es ingénieur, mais tout le monde t'appelle docteur,
Voilà, c'est ça.
alors tu n'es pas. Et tu veux être docteur. Tu veux travailler sur l'agronomie connectée, avec comme terrain d'expérimentation ton jardin au Chili. Alors on a bu quelques bières les pieds dans le sable, je vous donne l'image.
Sur la plage.
Et le lendemain matin, nous avions le feu vert de l'Université de Bordeaux pour t'accueillir. Je remercie par ailleurs Christophe et Guillaume qui n'ont pas hésité une seconde à t'encadrer sur ce sujet. Cette thèse a été l'occasion d'ailleurs pour nous de travailler ensemble. Et comme disait Guillaume, c'est la première fois on a un étudiant aussi expérimenté, mais c'est aussi la première fois que l'on travaille ensemble dans un tel cadre. Ensuite, tu as su garder, je dirais, le bon cap pour arriver jusqu'à ce jour, jusqu'à aujourd'hui. Et pour maintenir ce cap, tu as pu compter sur une aide précieuse de tous les jours que tu appelles ta motivation. C'est Maria-Louisa. Merci beaucoup, Maria-Louisa, d'avoir épaulé Victor, de l'avoir encouragé, et je pense peut-être même un petit peu rouspété. Je pense aussi à ton fils, Nicolas, qui doit nous regarder en ligne, et puis à Apollo aussi, qui aurait aimé être là. Alors, durant ces dernières années, tu as associé le laboratoire IMS à ta vie professionnelle et personnelle. Nous te remercions pour les événements que tu as pu initier et auxquels nous répondons toujours présents. Sessions spéciales, seasonal school, co-organisation d'événements. Et je te remercie aussi d'avoir toujours répondu présent à toutes nos sollicitations. Alors, au-delà du travail, il y a la camaraderie. Et c'est toujours un plaisir de se revoir, surtout en personne. C'est ça qui compte. Alors, d'ailleurs, je dois évoquer quelques souvenirs quand même de voyages en Amérique latine, comme au Chili, à Reñaca. Nous avons refait le monde. Bien sûr, on l'avait refait très bien, sans aucun doute, avec un cocktail de fruits et qui venait de Pessac, qui plus est, il faut le dire. C'est une soirée inoubliable. Ou encore, je pense que c'était plein, hein, mais un certain dîner de conférence à Bento Gonçalves, on avait vraiment bien. Alors, après, je peux parler aussi de chacun ici, où on s'est rencontrés au Japon, des repas à San Francisco et plein d'autres endroits où on s'est passé. Alors, pour conclure, je dirais simplement que le jour est enfin venu pour que tu n'aies plus aucun regret dans ta vie, que je suis très heureux de tout le travail que tu as pu faire, que l'Université de Bordeaux est vraiment honorée de te compter parmi ses docteurs, et enfin, que j'ai toujours et j'aurai toujours le plus grand plaisir de partager des moments conviviaux avec toi. Encore merci. Muchas gracias. Thank you very much.
Merci. Merci. Merci, François. And now the word is going to your PhD advisor, Professeur Gigot.
Victor, je vais également le faire en français parce que je sais que tu as la langue française. Alors, c'est jamais facile de passer après François, parce que François prépare bien les choses, François a bien raconté l'ensemble de l'histoire. Donc, je pense que je vais être plus bref. Comme François et Guillaume, c'est un petit peu bizarre de devoir encadrer, entre guillemets, mais c'est plutôt échanger avec quelqu'un qui a plus d'expérience que nous. Parce qu'il faut quand même voir que durant ces 3 années, ces 4 années, il y a eu beaucoup de questions. Et ce qui est aussi intéressant, c'est que finalement, à la fin, on a encore plus de questions qu'au début. Au fur et à mesure de tes propositions, finalement, ça soulève d'autres questions, d'autres questions, d'autres questions. Et tu étais toujours enthousiaste pour essayer d'avancer sur les différentes problématiques, que ce soit plutôt sur les aspects capteurs, comprendre le fonctionnement des plantes, ou sur les aspects électroniques, comment concevoir un système électrique. Là, c'était un vrai plaisir d'échanger avec toi. Tu voulais vraiment, comme dit François, faire une thèse dans les règles de l'art, comme on fait un étudiant plus jeune. Tu as répondu à tous les attentes par rapport à cette question. Et je vais terminer par ce que je préfère dans ta présentation. Ce n'est qu'un début. J'espère qu'on aura l'occasion de collaborer sur continuer et proposer des choses par rapport à ce cas.
Merci beaucoup.
Merci, Christophe. I would just stay there just to make a difference because I know that the camera is just looking at it. Thank you, Victor. Thank you so much. In the name of IMS Laboratory, to choose this laboratory to make this work, because I agree that with what has been said previously, this is a unique work. It paves the way for so many applications. And there is little things that really are vital for human beings, and eating is one of those. Drinking water, but not only, but also drinking and eating, that's really key. And I agree with you that we are not taking care enough of that problem that's going in front of us, not only because of climate change, but also because of the growing of the population and the reduction of the arable area, as you said. And electronics can definitely make something here and helps and brings a lot of things. You talk a lot about sensors, but we can also talk about actuators and, of course, closing the loop and paving the way to autonomous farming. For sometimes, if you had some artificial intelligence coming from the agronomist, not from the electronics, for sure. You can make the code, but they have to give us the algorithm. And this is things that really are of great level. Do you think that your chip, the current SOC, can be used for actuators as well as you develop it for sensors so far?
Yeah, I think they can be used for a lot of agricultural application, and this is the idea. At the beginning, I started with a very specific one for the crops grow, but after I can see that can be used in some other agricultural applications. So this is also the idea to put some peripherals very general, so we can put actuators and sensors at the center.
Okay, so that's really can create something which is of great interest. Thank you so much. We are now going to retire ourselves just a little bit if we have to give you the title of doctor, which I think has already been given by the most people. So certainly we'll be back quite soon.
On peut en mettre un. Industriel, peut-être se mettre là. Non, celui-là.
J'enlève mon masque. Je peux? C'est fatigant.
Non, c'est ici, oui. Moi, je serais bien ici. Est-ce qu'il y a Antoine qui est connecté
On va attendre. On va attendre.
On va attendre.
Vous me faites un signe, Rémi, quand il est là? So, Victor, as you can see, the decision of the jury has been taken very rapidly. And of course, the news that are coming are really good. But first, let us talk about your presentation. We all agree that you definitely make a very interesting work. And your contribution is unique. It's so special. Thank you so much for this work. You definitely paves the way for a new area of application for electronics and also a new era for agriculture, agri-food, and agribusiness. And your contribution have a very, very important social impact. And that's really something which is unique once again. And during the question and answer, you demonstrate a very professional answers to the discussion we had with the jury, and that demonstrate your extensive knowledge of your area of research. We also want to insist on the fact that you demonstrate a clear vision of the future and the future development in the area of agriculture and food and electronics. For all those reasons, the jury fully agree on attributing you the title of Doctor of the University of Bordeaux, and we give you the greatest warm and felicitation.
Thank you very much.
Thank you so much. Congratulations.
Let me finish, if I can finish with some words. I would like first to thank the board, and that is it's quite late for him, but I would like to really thank for all the effort here. I also would like to thank my advisors that worked with me for 4 years. It was very important and very interesting work, and I learned a lot. Also, I would like to thank my family for all the support I got from them. But the important thing is that we started a new topic that is very interesting, and I'm really looking forward to continue that work. That you know that we are already doing some stuff. I'm very proud and very excited today. I understand. So it is an achievement that I was looking. So I will say something 1 second in French because it's not sure that in English will go the same way. When people were calling me doctor, je ne suis même pas infirmier. Now je peux dire I'm a doctor. Thank you very much for all this. Thank you. Je voudrais, avant que vous partiez, bougez pas.